Hey scientists, this is Dr. B and we're doing activity 2 in what is the future of Earth's climate. We're on page 1. You can get here by going to learn.concord.org. The question of Earth's future climate is one of the most important unanswered scientific questions today. Let's start rolling the video while we read this. So this video is going to show us how the temperature has changed compared to the average over a period of many years, over 100 years here. So you can see the Earth's pretty cool at first. You can see this video goes kind of in 5-year chunks, a 5-year moving average. This means that the temperature for each 5-year period between 1880 and 2019 were averaged. The video shows how these 5-year temperature differences compare to the baseline temperature between 1950 and 1980. A lot of models use that base temperature because it's before the Earth started warming dramatically. And if you see the video right here, the northern hemisphere is much hotter than it used to be way back in 1880. Let's scrub back here on the video and watch it get cooler and cooler as we go back in time and get hotter and hotter and hotter. So this is about my lifetime. So the planet was pretty, cool. But now look at how hot it's gotten just in the span of one person's lifetime. In this module, you'll examine climate data and models and explore what we might be able to predict about the future. Climate affects all forms of life. It's an essential factor in determining how ecosystems work. Scientists know that the world has warmed over the last 10,000 years, and humans have contributed to that warming in the past 100 years. So the things that we're trying to predict is how warm will Earth get? How fast will Earth warm? What will the future climates be like? I'm only about halfway through my life, and in the next half of my life, how much warmer is it going to get? And you should be asking in your life, you're younger than I am, how much warmer is it going to get into my life, and how is that going to affect how I live here on planet Earth? So what do the colors indicate about the change in average temperature over time from 1884 to 2019? Here's your temperature scale right here. Here's 0. If it's sort of bluish white in this range, it's the average. The average was, the baseline temperature was between 1950 and 1980. So this compares it between 1950 and 1980. That base temperature is at 0. If it's hotter than that, it's red. If it's cooler than the 1950 to 1980 average, it's blue. So if you go back in time, it's cooler than 1950 to 1980 average. If you go forward in time, it's much hotter. In the past 50 years, where has the temperature changed the most? Well, you can look along the red zone here. It's the northern parts of North America, the northern parts of Asia, the northern parts of Iceland, and mostly the northern polar region. But also there's some stuff going on down here at the South Pole. All right, let's go on to the next page. So, trends of the past. The graph shows the temperature change anomaly from 1880 to 2019, comparing the average temperature from 1950 to 1980. So in this range right here, 1950 to 1980, they're considering this the baseline or normal. Each point on the graph is an average of the temperatures for the preceding 12 months. So say this point here in 2019, that's the average temperature for 2019. The red line here is the average for the 5 years before 2019. So we took 2019, 2018, 2017, 2016, and 2015. We took those 5 years, including 2019, we averaged them, and that's the red line right here. If we go back a year to 2018, we're going to average 2018, 2017, 2016, 2015, and 2014 to get that red line right there. And notice the red line and the black dots don't always line up, but the red line, since it's an average, running average of 5 years, kind of smooths out those ups and downs of this average temperature for each particular year. So describe the average temperature change from 1880, that's right here, to 2019. How much did it go up? It was a little below to all the way 1 degree Celsius. That's actually, it doesn't seem significant, but that's pretty warm. It means we have less snow, that summer is longer and summer is hotter. And winters are less cold. They don't kill off all the nasty bugs that kill trees in some places. This graph shows the global temperature changes again. Now we're going to focus on understanding the data a bit more. The black points show the same data as the last graph. That's per year, the average of those 12 months. The red line shows the 5-year running average computed for each year. So every year they take the past 5 years, including that year, and they make an average to kind of smooth out the data. The gray shading shows scientists' uncertainty with the data. So back in 1880, thermometers were built a little bit differently. Now we have highly accurate electronic thermometers that use difference in changes in conductivity to measure the temperature. But back here, we were using glass tubes filled with mercury. And we don't exactly know the conditions that people were taking temperature readings here. Now we're pretty darn sure what's going on. Why is the curve between 1950 and 1980 relatively flat and centered around 0 degrees difference from the baseline? Well, this is the baseline. 1950 to 1980 is the baseline. So right here, the baseline years aren't going to differ too much from the baseline. There are some that go up and down, but when you average them out, 1950 to 1980 is pretty much right at 0 because that's what we consider those baseline temperatures. That's what we compare everything to right now. Maybe in 50 years when you're teaching this lesson, they'll be comparing temperatures to 2000 to 2020 because it'll be even hotter. Who knows? The gray shaded areas are called error bars. They indicate the range of uncertainty that scientists have about the graph on the data on the graph. Why do you think these error bars are smaller in the late 1900s and 2000s than they are for the 1800s in early 1900s? Well, we talked about thermometers and how accurate thermometers were, how careful people are about taking temperatures, and we probably have many more points around the globe where people are actively monitoring temperatures all the time. Because now we have computers, we don't have to send somebody out with a glass tube full of mercury to take the temperature somewhere. We've got computers with automatically registering temperature sensors, all kinds of places, all over the world, and even all over my neighborhood. There are people who just have weather stations that they put the data out online so everybody can use it. Why is the black line so much more variable than the red line? And what's the difference between the data that they show? Well, the black line is every single year. It's the average for every single year. And so this is the average, say, for like 1982. Average temperature for the entire year of 1982. But this red line here is the average for, they took 5 years, 82, 81, 80, 79, and 78. Those 5 years, they averaged them, and that gave us our red line. When we get to 1983 here, that's for way down, but you took the previous 5 years, 83, 82, 81, 80, and 79, and you averaged those 5 years, and you still are pretty close to the 5-year running average of the year before. So that 5-year running average, that red line, that 5-year running average is called low S smoothing. So the smoothing line here, the red line, is going to be more in the middle because it's constantly averaging out. Where from year to year, the weather can get hotter or colder, and that can depend on ocean currents, can tweak the climate a little bit, tweak the weather from year to year. So the short answer is the black line is every single year, and the red line is an average, a 5-year average of that year and the 4 years before it. So how do we predict the future? We know the temperatures from 1880 to now, but how do we predict what the climate's going to do from 2025 to 2100? Nobody really knows what it's going to do, but we're all trying to figure it out because there needs to be changes in agriculture, changes in policy, changes in transportation. If the world's getting hotter, we need to be able to plan for that so we can keep people safe and keep people fed and have enough water. So it's important to be able to predict. So what is the overall temperature trend between 1880 and 2010? Well, if you look at this, it's going up. So it's warming. You can see this is the temperature anomaly, and that temperature anomaly keeps adding. It's adding to the average or the baseline. What was the temperature change between 1920, that's right here, and 2000? So from here to here. So 1920 it was -2, and 2000 was +4. So if we count here, 1, 2, 3, 4 tenths, 5 tenths, 6 tenths. So about 6 tenths, positive 6 tenths. So the 3 lines marked A, B, C on the graph are possibilities for what could happen in the future from 2010 to 2100. Which line best shows what you think will happen to the temperature in the future? So are you going to choose A? It's going to keep getting hotter. Choose B, we're going to take drastic measures, get rid of a lot of carbon dioxide, and we're going to somehow stabilize the temperature. Or C, somehow it's going to get colder. Now, question 10, you need to explain your answer. What do you know from the graph? What do you know from the rest of this activity about that supports your prediction? So you could say we know temperatures have been getting hotter from 1880 to 2010 by looking at the graph. So that's one way I can support my answer. HASBOT here is an automatic kind of grading machine, grading program that looks at how well you explain your answer. And it's going to tell you, it's not a 6 right now, that was my previous answer, how good that graph is. What we could do to make that answer better, which is will probably tell us if we just submit that answer, we could say we know the temperature went up 0.6 of a degree from 1920 to 2000. So the temperature went up 0.6 degrees. We're just going to assume that's Celsius because that's what scientists use, between 1920 and 2000. So we're going to give a specific instance of how much the temperature is going up. All right, we'll see how we do with that. And then our next mission here for HASBOT is to explain how certain we are about our claim based on our explanation. So we think line A, the temperature is going to keep going up. Our explanation is that the temperature's gone up in the past, so it probably will keep going up. And we know for certain that thermometers have been pretty good from 1920 to 2000. There's not as much uncertainty in that area. On the last graph on the previous page, let's go back and look at that. The uncertainty from 1920, we can just say the uncertainty from 1980 to 2020 is really pretty good because we have better thermometers. So you can see that gray kind of smushy stuff. That means if it's pretty tight to the data, that means we're pretty certain about that data. So from 1980 to 2020, there's a lot of certainty about that data. And that's when the temperature has been increasing the most. So let's go back down here to our answer. The certainty rating on the temperature readings from 1980 to 2020 is high because thermometers were more reliable and more accurate. We can take a temperature now to like hundredths of a degree. That's hard when you just have like a glass tube with mercury in it. So I'm not giving a complete answer here. I'm not going to do very well with HASBOT. I'm going to submit this and see what HASBOT says. I did okay. I got a 4 here. But the important thing is give it a couple tries and use this feedback. Can we think of any factors that affect Earth's temperature? What do we know about the science behind this graph? How might those factors affect your prediction about future temperatures? Like, do we know how much carbon dioxide's in the air? Do we know how much water vapor's in the air? Can you explain what about the graph makes you certain or uncertain about your response? Well, sure I could, but I'm going to let you do that. And I'm going to let you improve these 2 answers so that you get a better score when you resubmit them. So pause the video, rewrite question 10 and question 12 to see if you can get a better score. Challenge yourself to get a 5 or a 6 and at least a 3 over here. Way back in time. So this is a Vostok ice core. And an ice core is like kind of like sticking a very large straw into the ice for several, maybe hundreds of meters to bring up ice that's really, really old, that formed thousands and thousands of years ago, and the snow is really smooshed. The data for previous graphs were obtained by thermometers, but what if scientists want to know the Earth's temperature before humans started collecting data? These ice cores are a way to see how the climate has changed over hundreds of thousands of years. By studying glaciers and ice sheets, scientists have been able to infer global temperatures. So we look at the amount of carbon dioxide and other aspects of the ice, and we figure out what temperature we think it was based on that, the carbon dioxide, minerals, and other factors. Scientists take cores of the ice by drilling holes deep into glaciers and ice sheets. Since layers at the bottom are older than layers at the top, scientists can see the changes in the trapped gases over a long period of time. The picture shows a 19 centimeter long section of an ice core taken from the Greenland ice sheet. Why do you think the winter layers are darker than the summer layers? Now that's a really good question. It turns out in the place where they took this ice core, it actually snows more in the summer. And the summer snow is cleaner, so it ends up being whiter. So these white bands are the summers. These darker bands are the winter snow. And since there's less winter snows, it swirls around more and mixes with more dirt, more minerals, and that snow is dirtier, so it appears darker in the ice core. So the darker stuff is kind of winter, dirtier snow, and the lighter stuff is summer snow, where more of it fell and it was compacted more quickly. So it stayed cleaner. Vostok Research Station. So here's our Vostok ice core data. The data goes back 420,000 years. So this is 0 years ago. That's kind of right now here. And here's 450,000 years ago. This comes from the Vostok Research Station in Antarctica. The graph shows the temperature change from 420,000 years ago to now. The temperature on the graph shows a change of -3°C or lower. Earth was in an ice age. So when we go below -3 here, we're in an ice age. Anytime you're below this line, you're in an ice age. Anything above the -3°C line right here is an interglacial period, which means between the glaciers. So it's warm and kind of like today. The trend in the graph shows short warm periods between long periods of highly variable cold climate. Which statement is supported by the information in the graph? Well, you can come up with your own conclusion there. So now we're going to kind of compare these two graphs and put what we know together. So describe how the climate trends from 1880 to 2019 might change the pattern of warming and cooling shown on the Vostok ice core graph. So the Vostok graph usually goes up and down and up and down and up and down. But here, so we're kind of based on the normal pattern we see here, after spiking the carbon dioxide, we should start heading down. Temperatures should decline, but we're not. We're hanging right here at 0. And this corresponds with this kind of chunk here. This is not headed down because this is headed up. We're getting hotter, and so the ice core, the temperature is not going down. And you can write up your own version of that. So if we want to predict the future climate, by simply looking at the changes in temperature isn't enough. The Earth is really complicated. Scientists use mathematical climate models to try to predict what's going to happen in the Earth's temperature in the future. The math is very complicated because you have lots of variables, so scientists use computer programs to do their calculations. So here are a couple of predictions here. Some people think it's going to get much hotter. Some people think we might kind of stabilize a little bit. But everyone agrees that the temperature is going to continue to rise into 2100. Scientists designed their models to focus on just a few of the components at a time. In the next 4 activities, you'll see use climate models to understand how the global temperature is affected by changes in the mix of gases in the atmosphere. So activity 3, 4, 5, and 6, you're actually going to be using models to do what scientists do and figure out how much the temperature is going to increase. Although scientists generally agree that global warming is occurring, there's still many unknowns about what exactly will happen to Earth's many climates as a result of global warming. So there's always new things that we didn't remember to put in the model. For example, until a few years ago, people sort of forgot to take into account that water, even when you heat it up a little bit, expands just a little bit. And that's not a big deal if you just have a glass of water or a cup of coffee. But if you have an entire ocean and it even expands its volume a little bit when it gets a little bit warmer, that means the oceans rise. Some of the models didn't include the permafrost melting and that carbon dioxide being added. Permafrost is permanently frozen soil that has some dead plants in it. And once that warms up and stops being frozen all the time, like it is in Alaska and Greenland, that decaying plant material and all the swamps, it's going to start to rot and add even more carbon dioxide. So there's all these factors that folks are just we keep figuring out things that we need to put in the models to refine our models. So there's always a little bit of an uncertainty in our models because we don't have all the variables yet. We're still discovering them. This is the largest experiment humanity has ever done. We don't know what we're going to do to our planet. And so we're going to try to learn some about it so we can understand what's going on. So, activity 3, you can check out those videos. If you want to download your answers from activity 2, go to Show All Answers on your iPad. Find the little box with the up arrow in it. Click that. When you click that on your iPad, you'll get a little box. It'll have a blue word that says Options. Click the Options, click PDF, click back out to the menu, and then click Notability. Thanks so much. I'll see you in activity 3.